again. I will be very quick. I will not take the full half an hour because people like already are to go to lunch because quite hungry. Hello again, I'm Giuseppe. I'm the head of the Space Science and Innovative Application at Giant, and we'll talk about the space applications using ground-based radio telescopes. So this talk will be about this observational spacecraft using the LBI radio telescopes and their scientific applications. It's a technique that we developed at Jive, and it has application from navigation, like GPS style, but in the solar system, to weather in the solar system. It opened the VLA community to different fields like planetary science and fundamental physics, and I will talk about the synergy with other fields and the synergy with Argos. So, what's the difference between how can we do the LBI with the spacecraft? What's the difference with the classical LBI? So, the spacecraft are in the so-called near field. So, you assume usually that your source is very far away. And your wavefront is parallel to the city's plane. But for the spacecraft, you have to take into account that the light from the spacecraft reach the two antennas at different times because the spacecraft is too close, and you take into account of this additional delay. So this is called near field delay, and near field delay model for your colleague to take into account these effects. So why we do these observations? So we developed a technique called a planetary radio interferometry Doppler experiment, PRIDE, and it provides the state vector, high accuracy estimate of the state vector of orbiter landers in the solar system using the LBI. That can be used for a variety of scientific applications, like winds in other planets or moons, internal structural composition, the ephemeris of this moon, and so on, up to general relativity experiment. And so the first experiment that we did with this technique was the landing of the Huygens probe in the Titan atmosphere. So we use we feedback on the interspacecraft communication. It was the Cassini spacecraft that sent the probe that descent on Titan, and they were communicating with the S-band link. So we observed the S-band link between two spacecraft while the probe was descending on Titan. And on the top right, you see our measurements in three dimensions, and you see the movements, lateral movements of the spacecraft descending on Titan due to the wind. So we could measure the wind speed on Titan using the LBI observation from Earth. And that was very useful because they had an issue with the Doppler wind experiment on board. So with our technique, we could help them to recover some of this information. And the wind was quite high, it was about 230 kilometers per hour, so pretty windy day. So from this experiment, we developed a technique, and we used for many experiments that I will show later. We are now official part of the mission. While on the Cassini-Huygens experiment, we were just saying, okay, can we do that? We talked to ESA, NASA, and they say, okay. But now we are an official part of the mission. We are one of the experiment of next flagship mission of ESA, the JUICE mission, that is on its way to Jupiter. Our experiment is called PRIDE, it uses LBI, and we produce ephemeris. Jive is the PI of this experiment. It's an experiment, it's a mission that we try to answer the question if Jupiter system are habitable worlds. And our small contribution will be improving the ephemeris of the satellites. You see all the others scientific questions here in these slides, but the important answers that our measurements could help to find. It's about constraining the orbit evolution of a satellite system, studying the evolution of the moon. That's if you know better where these things are in space, so better ephemeris, then you can answer this question, determine better the Jupiter mass, and if you improve the astrometry from data from 1873 up to the Gaia data and planning future mission. The plot there is the signal of JUICE 2 days after it was launched. Observed we got 12-meter antennas from the University of Tasmania, our collaborators. So it doesn't use our technique any onboard additional instrumentation. We use just the ultra stable oscillator on board that is already there for telecommunication or for other experiment. So we use that and we do our experiment. So in case of Huygens, it was a distance of 8 astronomical unit. It was S-band. It was not a frequency that our radio telescope were tuned for. And so at the end, we got an accuracy of about 1 kilometer in the plane of the sky. For JUICE, now we are part of the mission from the beginning. The band is X-band, and with a time resolution of about 10 seconds, we can obtain a resolution of less than 100 meters. And if you go to Ka band, it's about 20 meters. This data will help improving the ephemeris, and the bottom table shown in red. When you have an off-plane orbits of your satellites, you have an improvement of about 80% or 70% or 95% in case of Callisto on the accuracy of the ephemeris. Other experiments. So now we are in that experiment. It's in the future. We'll arrive to Jupiter in 2030. I'll just show you briefly other experiments. Like this one was a track campaign of the Venus Express from ESA, a spacecraft orbiting around Venus. At a certain point, they lower their orbit, so the spacecraft passed through Venus' atmosphere, and of course it slowed down because of the atmosphere. And we measured that slowdown. You can see in the single Doppler plots, where you see the dip, and you have the VLBI images on the top right of Venus Express along the orbits, and the comparison with the data from the tracking station from ESA. So we got a Doppler frequency drop of about 40 millihertz and precision in the velocity of 1.1 millimeter per second. So while you go down in the atmosphere, in this case with an occultation, you can study the composition of the atmosphere because of the characteristic of the changes of the received signal. Here you have the plots of refractivity, neutral number, and density, and at the end, using these the temperature and pressure profiles. And I show this because you have the data from the tracking station of the radio science experiments, and then you have our data that go a bit deeper because we have a better geographical distribution of our telescopes. And also, the first plot showed the dip of the signal through a complete occultations. So even if the spacecraft is not visible anymore from Earth, due to the propagation to the atmosphere, you could observe the signal all the time. Another experiment was the flyby of Mars Express. This was a huge VLBI campaign. We got more than 30 telescopes all around the world, observed for 26 hours for 2 orbits around Mars. These are our results. The map there is Mars Express mapping with VLBI. And we have the 2 bottom plots are the VLBI displacement compared to the nominal position, and the Doppler, the convection noise in Doppler. So the accuracy that we got in the right section and declination was about 35 and 60 meters. and in a Doppler, it's about 30 micron per second. So very accurate measurements. So you can do spacecraft astrometry. We are doing the same thing for other spacecraft. We are observing baby Colombo in its journey to the Sun and Mercury system. And we are collaborating with NASA to observe the insights for their experiment about the earthquakes on Mars. And I want to show this plot because it's very crowded on Mars. So you just point your telescope there, and you get to 1, 2, 3, 4, 5 spacecrafts. And you can do a lot of things with 5 spacecraft altogether around orbiting the same orbit. Since the signal propagates in the solar system, we are affected by the solar wind, and the top plot shows in blue the signal when the spacecraft is a high solar radiation, far away from the sun, and the red one is when it's closer to the sun in the line of sight, and then you see a lot more scintillations. And the bottom plot is trying to disentangle between the ionosphere, troposphere, and the solar wind. So what we do with this data, you can do interpretary scintillation studies, solar winds, and then the effect on the communications and coronal mass ejection. This is, we are collaborating with our Chinese colleagues, and this is an experiment from Ma et al. That we did together with the EBN, and we observed with the ABI both Mars Express and the Chinese Mars orbiter Tianwen, when it was very, very in opposition to the sun, so very close to the sun, to study the effects of the solar wind on the system, to study the warm region of the solar wind. Another application is the coronal mass ejections. So that was by chance doing one of those observations. We noticed that the difference of like a couple of days, even if the source was the spacecraft was more or less in the same position compared to the sun, we have a completely different pattern in the scintillation, and that's why there was a big plasma blob, coronal mass ejection, that passed in front of the spacecraft signal while we were observing. And you can make some models and extract the size and the composition of this plasma cloud. Fundamental physics, we know while radioastronomy space VLBI telescope was active, it has a mixer board, a nitrogen mixer. So we try to do a fundamental physics experiment to measure the violation parameters of the equivalence principle. And there is a paper about our results with the Doppler measurements, and there will be a follow-up that will use the VLBI measurements to even improve further the accuracy of this detection. In the past, we observed also the GPS spacecrafts, Galileo, GLONASS. You can do observation of these spacecraft around here. So we moved from Saturn, Jupiter, the solar wind, Mars, Venus, and now we are around here. And you can link the celestial frame to the frame for the GPS. You can do by static radar, even closer. You can observe a near-Earth object, or on the right side, you have the micro-Doppler signature of a rocket body. So it's a piece of a rocket that was observed with it. So you can do a space debris in this VLBI tracking. And so very quickly, so almost at the conclusions, these are the possible synergies of space application in Argos. So what I described up to now were mostly higher frequency observation that use X-band from the spacecraft. There are other spacecraft transmitting at a different frequency. You can do spacecraft tracking at lower frequency, like at 1 gigahertz, L-band, and X-band. You can do scientific experiments with those. And there are CubeSat and NanoSat that may need orbital measurement, like a service, or you can do scientific experiment while these spacecraft, while this small probe are around the near solar system. You can do, we are working together with law firm. We have a very good space for the group, and we try to do simultaneous observations of the spacecraft during one of the space weather campaign. And you can do space debris mapping. If you have a radar that transmits the frequency, then you can observe the bouncing static mode. And SETI is a best application. You can do like high resolution localization of a SETI signal at a lower frequency, or using the interferometer to suppress the local RFI. These are my conclusion that I here just show the possible applications and the possible synergy with Argos. That's it.
Yeah. So I didn't, because I didn't see the part of how you process data. So I assume some of them are real-time tracking.
It's hard.
Real-time tracking. When you're tracking the baseline value in real time.
We're tracking real time?
Yes. So how to process the real data then in real time?
Oh, no. You could do real time, and we are working on that, but it means that you have to have like a real time correlation, like VDMO, but no, we don't do that. The one of almost real time was the one from the Cassini audience, but at that time they were still dishes, disk racks, and to do the observations, to do the correlations as soon as possible. There were people in Australia on a small plane going from one telescope to another one, collect the disk, and then fly back to Sydney, put them mounting on a rack, and then do the heat transfer to Jive, where we did the correlation. And then after a couple of hours, then we got the detection. But real time is possible, but not yet tested.
So let's see if there is any question from the online audience. Otherwise, we can continue the discussion outside. Any questions from the people online? Right. If not, I think we can meet again here.